Welcome to Concentration Units 3, Converting Among Our Units. So in our previous videos, we worked on the skills in blue. This video is going to focus on the one new skill, converting among all of our concentration units. So before we do that, let's take a look again at our concentration units. And note again that we've got different units in the top and in the bottom. We're going to be converting these units that have both a numerator and a denominator. So we're going to focus on converting one of those at a time, and we can do them all with dimensional analysis. So here's how it's going to work. So for all of our concentration units, the solute is in the numerator. It is the part that we're interested in. And those units are either in moles or in volume units or in mass. So those are all units that we know how to convert among. So we know how to get from moles to mass with molar mass, and we know how to get from volume to mass with the density of our solute. It's the denominator that's going to be a little trickier for us. So in the denominator, those units either involve the solution or just the solvent or a sum of what's going on with our solute and our solvent. And those units are varied, and some of them we can convert between and some of them we cannot. So we can convert between the liters of our solution and the mass of our solution if we know the density of that solution. But we really can't go between the liters of the solution and the kilograms of the solvent. So that little dashed line there is an approximation that we can make for dilute aqueous solutions, which is a pretty common situation that we have. So if we have a solution where water is our solvent and the concentration isn't very large, so it is quite dilute, we can approximate that the liters of the solution is approximately equal to the kilograms of that solvent. If we need to deal with total moles of things, then all bets are off. Then we have to go back to the beginning and recalculate based on knowing what went into that solution. There isn't a straightforward, simple conversion there. So here's one of those conversions that we can do, and it is very similar to one that you did in your lab with the vinegar titration. It's converting between molarity and mass percent. So here's our question. We're going to convert 0.85 molar calcium chloride to mass percent. And the extra bit of information that we'll give you is that the density of this solution is 1.08 grams per milliliter. So remember, that's the density of the solution. That means there's 1.08 grams of our solution, the complete mixture, for every milliliter of that solution. So when we use that density, we have to make sure we're using it correctly. So it's going to be very important that you're keeping track of what are both the units and the material that is being referred to. All right, so we're going to start with 0.85 moles of calcium chloride per liter of that solution. So I'm gonna write that molarity with both of its units, so we can clearly see the numerator and the denominator, so we can see what those units are and how we might want to convert them. Okay? And we're trying to get to mass percent, and mass percent is grams of our solute for every 100 grams of our solution. All right, so if we take a moment and look at the numerator, it starts out as moles of calcium chloride, and we want it to end up as grams of calcium chloride. So we should be able to do that conversion using molar mass. In the denominator, we need to convert between liters of our solution and grams of our solution. So that's a volume of one material and the mass of the same material. So if we know the density and can get all of our units compatible, we should be able to do that lower conversion as well. Okay, so this will allow us to practice conversions where we're changing both a numerator and a denominator. All right. So here's what it looks like all done in one sort of linear dimensional analysis problem. So that first parentheses is the conversion factor for our numerator. It's changing the moles of calcium chloride into grams of calcium chloride using the molar mass of calcium chloride. So we had to go and figure that out from the periodic table. The next two conversions are for changing the denominator. So again, we just have to kind of watch where we put those units and be a little more careful. So we had to change our liters into milliliters using a prefix, and then we can use the density, which involves units of milliliters and grams, to convert to grams of our solution. And if we stopped right here, we would have moles of calcium chloride per gram of our solution. But note that we want this per 100 grams. So we have to do one more thing, and that's to multiply by 100% to get us on that percent scale, the how many out of 100. And when we carry out that calculation, we are limited to two significant figures by our original molarity. We have 8.7% by mass. All right. So we'll try a different one with a new unit of concentration, parts per million. That's that ppm. That means how many out of a million. So just like percent is how many out of 100, ppm, or parts per million, is how many out of a million. All right, so let's look at what we have here. So the recommended concentration of fluoride in drinking water is 0.7 ppm by mass, and we want to know what is that concentration in molarity. So we'll do the same thing. We're going to write out what our original concentration is, numerator and denominator, and then look at what units we're trying to convert it into at the end of the day, numerator and denominator. Okay, so 0.7 ppm means there's 0.7 grams of fluoride for every million. So that's 10 to the 6th grams of our whole solution. So again, remember, just like percent is how many out of 100, ppm is how many out of a million. If we had ppb, parts per billion, it would be how many out of a billion, or 10 to the 9th. All right, so in this problem, we are changing it to molarity. We want to end up with units of moles of fluoride per liter of solution. All right, so again, we'll do the same approach we did in the last problem. Look at the numerator. They both refer to the fluoride ion. We start with grams, and we want to end with moles. So we need to think about how we can convert between grams and moles. In the denominator, we need to get from grams of the solution into liters of the solution. So here, think about the conversion factors you're going to need in order to make that change from a mass into a particular volume unit. All right, so here it is all worked out. So we start with our parts per million, 0.7 grams of F minus per, or divided by, 10 to the 6th grams of our solution. So again, that first conversion factor in the parentheses is just converting the numerator. So we're just focused on the numerator one at a time. And there's 1 mole of fluoride contains 19.00 grams of fluoride. And then the next two conversion factors are strictly done to convert that denominator, that grams of our solution, into liters of the solution. So we did need a density in this problem. We needed to know the density of our whole solution. So again, this is a very dilute solution. The concentration is not very large. That's why we're using the units of parts per million, which is for very low concentration things. So in that case, we can assume that the density of our solution is very close to the density of just the pure solvent, which in this case is water, since we're talking about drinking water. So for the density, we can use 1.00 grams per milliliter. That's roughly the density of water. And then lastly, we need to convert into liters, so we need to use our prefix conversions again. All right. So again, remember we used our approximation here that for a very dilute aqueous solution, the density of the solution is approximately equal to the density of water. So that is the approximation that we used, and certainly the three significant figures, that is a valid approximation. All right, and we get 4 times 10 to the minus fifth molar, right? Moles per liter, so we can shorten that to just the capital M for molarity, right? And again, note that it is a very low concentration as expected. Well, thank you for joining me for Concentration Units 3, Converting Among the Units. I hope you had a good time reviewing our concentration units from this series of videos and learned about a few of our new units. See you soon.